Up to this point, we've been focused on the tabular data model, in which we're storing attributes in an information system like a spreadsheet. The geospatial data model builds on the tabular data model, in which we're not only storing attributes, but geographic features as well. Now, when we're modeling geospatial data, we go through the same process in which we create a conceptual data model, a logical data model, and a physical data model. But in a geographic information system, we need to consider the geographic location of our entities as well. So for example, in the conceptual data model, we model the user's view of the data and define the entities and relationships, but we also need to conceptualize how the location of the features relate as well. So in this example, it's not just persons, buildings, and parcels, it's persons own buildings that reside on parcels. In the logical data model, we need to select the geographic representation as well as the tabular attributes. And the geographic representation might be, for example, representing a building as point and a parcel as a polygon. So once we've conceptualized the user's view of the data by selecting the entities and the relationships, the next step in the logical geospatial data model is to select the geographic representation. And we have three basic models that we utilize: vector, raster, and triangulated. And if you look at this example, you can see that we're mapping the exact same area with vector data, raster data, and triangulated data. And not one data model is necessarily better than the other. It just depends on what we're trying to accomplish. So with vector data, it's focused on modeling discrete features with precise shapes and boundaries. In this case, for example, using points, lines, and polygons. We've got polygons that represent lakes. We have a stream that is represented with lines, and it looks like there's a point there that maybe represents a location within that green space. Raster data is focused on modeling continuous phenomena. So in the example above, we're still modeling the exact same area, but now we're using rows and columns of cells that represent a single entity, in this case, land cover. So it's not just about the lake and the creek, but it's also about the open space and the developed area as well. Last, triangulated data is focused on an efficient representation of a surface that can represent elevation or other qualities such as concentration, utilizing triangles, or what we refer to as faces. So again, we're mapping the same area, but in this case, we're really focused on the topographic nature of the area and how the water, for example, flows over the surface into a creek and then pools in the lake. Once we've conceptualized our geospatial data and selected a logical representation, the last stage in the geospatial data modeling process is to select the physical data model. And you can see a number of physical data models categorized here as vector, raster, and triangulated. Vector data, again, are discrete points, lines, and polygons, for example. Some common formats include the ESRI geodatabase. There are different formats of that, which include a personal geodatabase or a .mdb, a file geodatabase, which is a .gdb file, or an enterprise geodatabase, which is a geodatabase stored in a relational database management system, or RDBMS, like SQL Server or IBM's DB2. Now, the geodatabase itself is not a vector data model. It's the feature classes that are stored in a geodatabase. Now, a precursor to geodatabase feature classes are ESRI shapefiles. That is a vector file format that stores both features and attributes in a file system. Every shapefile includes at least these three files: an *.shp file, an *.dbf file, and an *.shx file. The *.shp or shape stores the feature geometry. An *.dbf or database file stores the attribute values, and an *.shx is the index that links each geometric feature in the shapefile with each attribute value in the dbf file. Now, an ESRI coverage is a format that we don't see so much anymore. That was the precursor to the geodatabase and shapefile that was common in the late 80s and early 90s. This format, if you run into it anymore, you're typically converting that as quickly as you can into, for example, a geodatabase feature class so that you can edit and manipulate the data. Some non-ESRI vector formats include MapInfo, which is a smaller competitor to ESRI's ArcGIS in which they have a competitive edge both in the real estate and in the marketing industry. And so you might run into an asterisk.mif file. If you're working with engineering data, you might be working with computer-aided drafting like an AutoCAD drawing file or a MicroStation design file. Those are vector formats. And even Google has a vector format known as a .kml or keyhole markup language, in which they store points, lines, and polygons along with the symbology. And the compressed version of that is a KMZ. And then we're more and more working with LiDAR data or a .las file, which at first glance looks like a continuous geospatial data model. But if you zoom all the way in, it's just a whole bunch of points that store the X, Y, and Z, which is the elevation data. Some raster physical data models include an ESRI grid, which is an older format, but still used very commonly because it's just arranging data in rows and columns. It's very easy to utilize. In a geodatabase, we can store a raster data set. A digital elevation model is a raster format that was developed by USGS to store elevation data. And then there are a whole host of raster formats that store image data, like a tagged image file format or .tiff or a JPEG or a PNG, which is a portable network graphic. For triangulated data, there are really only two types of geospatial data models that we utilize. One is the ubiquitous triangulated irregular network, or TIN, which is utilized by not just GIS software, but CAD software and any type of 3D modeling software. And then in the ESRI products, we also can store triangulated data in a terrain object that is stored in a geodatabase. The geospatial data model is differentiated from the tabular data model, and not only that we're storing geospatial features as well as the attribute values, but also we can maintain the relationship as a spatial relationship or an association or interaction between the entities based on location. And there are different types of spatial relationships that we can monitor, including topological, directional, distance, and class. Topological is the relationship between features based on their connectivity, whether, for example, they're coincident or equal. For example, points are stacked up on each other, whether features intersect, or maybe whether one feature contains another feature. The spatial relationship can also be based on direction, whether one feature is northwest or south or east of another feature. It can be based on distance, how far features are from each other, or even class, how points relate to lines and lines relate to polygons, for example. And that wraps up our discussion on data models. At this point, you should be able to describe the components of the entity relationship model, including entities, the objects in the real world that you're modeling, relationships, the associations or interactions between the entities, the attributes or characteristics or properties of an entity, the definition, which is the structure for storing the entities, relationships, and attributes, and finally the format, the structured data encoded in a computer file. You should be able to label the symbology used in an entity relationship diagram. You should be able to explain the data modeling process, including the conceptual, logical, and physical data models. You should be able to list the three basic geospatial data models, including the vector, raster, and triangulated data model. And last, after completing the demonstration and project, you should be able to use an entity relationship diagram to model a database.